Morning students, my name is Dr. KCH Apparao, working as an associate professor in mechanical department. So today I would like to explain about three laws which are used to explain the uh, or measure the radiation or emissive power of radiation. It means rate of heat transfer by the radiation. We can say simply. So these three laws mainly Max Planck's law, Wein's law, and the third one is the Stephen Boltzmann. Okay. So next one we'll see the Kirchhoff laws also. So before going to this topic, just I would like to explain the previous important points which are covered in the previous class. Okay. So you know that radiation, yeah, it is just like little bit separate mechanism or a distinct mechanism compared to conduction and convection. Because in conduction and convection, medium is required, but in case of radiation, no need of any medium. Okay, so radiation also takes place in the vacuum condition also. So medium is not required. So the energy transfer by radiation is fastest, and it does not suffer any attenuation even vacuum. So there is no just a problem in the vacuum also. You know that fasting means the fast of energy by radiation. So that is equal to light velocity, that is the 3 into 10 to the power of 8. You know, 1 angstrom. This is the value already covered in previous classes. So further, it is also interesting that radiation heat transfer can also occur between the two bodies separated by medium. So that is colder than the both the bodies. It means radiation occurs in the vacuum as well as radiation occurs in the medium also. But medium does not influence the radiation. Radiation, it means energy transfer by radiation. For example, just like energy emitted by sun reaches the surface after traveling through space. So it means here radiation takes place in the space as well as in the medium also. So when the radiating energy from the sun to moon or sun to earth. So the radiation or energy transfer from the sun to earth. So two types of just like it means radiation transfer through vacuum, and the radiation occurs also in the medium also, just like extremely cooled air layers at altitude. So but these medium does not influence the radiation. So these are already covered in the previous classes. Okay. So next so radiation is the electromagnetic wave phenomena. So the phenomena of the radiation or heat transfer through radiation is the electromagnetic wave phenomena. In case of the conduction and convection, the phenomena of conduction is the just like lattice vibration and the free electron movements. You know that. In case of convection, the phenomena of radiation is the just like bulk movement of the particles. Similarly, the phenomena of radiation is the just like what is it? Electromagnetic wave phenomenon. Okay. So to explain the propagation of radiation, there are two theories are there. So one is the Maxwell theory, and another one is the Max Planck's theory. So according to Max theory, according to this one, the energy is transferred from hot body to cool body in the form of electromagnetic waves. Electromagnetic waves according to this one. So that is the lambda is equal to C by nu. C is the 3 into 10 to the power of 5. So electromagnetic waves are characterized by frequency and wavelength according to Max theory. Okay. So Max Planck's theory, you will see. According to Max Planck's theory, The thermal radiation takes place in the form of discrete quanta. So it means energy transfer in the discrete quanta, that is nothing but photons. So energy transfer in the form of the photons. So we can find out the emissive energy. So E is equal to h nu formula, and h into nu is equal to according to Max, so Max theory, hc by lambda. So this is the formula according to Max Planck's theory. Okay. So you know that a radiation emits from one body and reaches the another body. When the radiation energy reaches the another body, so three things will be happen. One is the absorption, and second one is the reflection, third one is the transmission. So this one also explained in previous class. Okay. So these are mainly depend upon the behavior of the surface of that body. So alpha represents the absorptivity, and rho represents the reflectivity, and tau represents the transmissivity. Okay. So it is depend upon the behavior of body. Suppose if you take the black body, just black surface, so total emitting energy, so which is reaches that body, that this energy completely absorbed. So that is the it means absorptivity alpha is equal to 1. So that is called black body. So if the emitting energy completely reflected, so that is the just like rho is equal to 1. So that is called white bodies. Okay. If you consider the just like glass bodies, so the complete emitting energy is transmitted through that body. So in that case, tau is equal to 1. If you consider opaque bodies, just like metal surfaces, so some absorption is there, some reflection is there, so there is no transmission. Okay. So some bodies you can observe some portion of absorption, some portion of reflection, some portion of the transmission. Okay. So these things also are covered in the previous class. Okay, now we'll see three laws. So Max Planck's law. Second one is the Wien's law. Third one, the Stephen Boltzmann law. Okay. So first of all, we will see what is the importance of Max Planck's law. According to Max Planck's law, how can we find out the emitting energy? What is the formula for the emitting energy by Max Planck's law? Second one is the how to find out the emitting energy by Wien's law. So last one is the Stephen Boltzmann. So three laws are there, but in conduction, so we use the only Fourier's law to find out the rate of heat transfer. Okay. In convection, just we have used the only Newton's cooling law to find out the rate of heat transfer. But in case of radiation, there are three laws to find out the emissive power. So what is the difference between these three? So what is the importance of these three laws? Okay, we will discuss about this one. Okay, first of all, we will see the Max Planck's law. Okay. So Max Planck's law, by the help of the Max Planck's law, you can find out the spectral emissive power. Spectral emissive power, simply called as monochromatic emissive power. Monochromatic emissive power means emissive power at particular wavelength. So the spectral or monochromatic emissive power for a black surface is highest at every wavelength. So at any given temperature. Okay. So that is the that was just explained by the Max Planck's law distribution. So these are the maximum emissive powers at particular wavelengths. Okay. It means finally Max Planck's law is used to find the emissive power at particular wavelength. Okay, it means emissive power at a given wavelength or emissive power at a separate wavelength. So at particular wavelength, we can find out the emissive power by the help of the Max Planck's law. Okay. So according to this Max Planck's law, EV lambda, emissive power at particular wavelength, is equal to C1 by lambda to the power of 5 into exponential of C2 by lambda t minus 1. So this is the formula, derived formula, just like here C1 and C2, those are constant values, C1 and C2. So C1 is equal to 3.74 into 10 to the power of 8, and C2 is equal to 1.438 into 10 to the power of 4 okay, micron and K also. So these are the just like constant values. Then you know that lambda is the given wavelength, so particular wavelength. T is the absolute temperature of the black body. Okay, so we can find out by using these values. We can find out the emissive power or monochromatic emissive power or spectral emissive power. Those are called the emissive power at particular wavelength. We can call this one. So spectral emissive power, it is represented by E by lambda, is the amount of radiation energy emitted by black body at an absolute temperature T per unit time, per unit area, and at particular wavelength. So at particular wavelength is very important. Okay, at particular wavelength, you know the wavelengths already covered in previous classes also. So what is the range of electromagnetic thermal wavelength band? Okay, so it means emissive power at particular wavelength, EV lambda, we can solve by the help of the Max Planck's law distribution. So second one is the Wien's law. What is the importance of Wien's law? Okay, it means just like according to Wien's law provides the wavelength where the spectral radiation or spectral radiance has maximum value. So if the spectral or monochromatic emissive power, the maximum value means so EB lambda is the maximum at lambda max. Okay, so it means it provides the wavelength where the spectral radiance has maximum maximum value. So it means that wavelength is nothing but maximum wavelength, that is simply represented by lambda max. Okay, so it means you can find out the lambda max. By the help of this lambda max, you can find out the maximum monochromatic emissive power. It means EB lambda max. Okay, EB lambda max, we can find out that one. So okay, so according to Wien's law, that one relationship has been given, that is the lambda max is equal to 2897. It was derived. So 2897 by T is the temperature of the body. Then T is equal to you can rewrite like this one. T is equal to lambda max into 2897. This is the value. Okay, if you substitute this lambda max value in Max Planck's law. So what is the Max Planck's law? EB lambda is equal to C1 by lambda to the power of 5 exponential of C2 by lambda t minus 1. Okay, if you substitute this lambda max value in this place of the lambda, we will get the EB lambda max. It means maximum monochromatic emissive power or maximum spectral emissive power. So you can see here also. Here just like so you know that formula. What is the formula? Just Max Planck's law formula, that is C1 by lambda 5 into exponential of C2 by lambda T minus 1. So here just like if you substitute the value of lambda max value, that is a 2897 by T. If you substitute this value lambda, okay, in place of the lambda, we will get the final formula, that is the EB lambda max. EB lambda max is equal to 12.87 into 10 to the power of minus 10 into T to the power of 5. So this is the formula. So it means finally, by the help of the Wien's law, we can find out the maximum monochromatic power, maximum monochromatic emissive power. So that is simply represented by EB lambda max. Okay. Depends by the help of the Plancks law, we can find out the emissive power or spectral emissive power or monochromatic emissive power. Monochromatic emissive power or spectral emissive power means emissive power at particular wavelength. Okay, here. So by the help of the Wien's law, emissive power at maximum wavelength. So that is nothing but maximum emissive power. Okay. So these 2 points you have to remember that. So monochromatic emissive power, maximum monochromatic emissive power, or a spectral emissive power, or a maximum spectral emissive power. Okay. So emissive power, monochromatic emissive power will be find out by the help of the Plancks law, or formula which is given by Plancks law, and maximum in monochromatic emissive power. So we can find out the value by the help of the Wien's law. Okay. So because we saw that 4 years law, only one law for the conduction, Newton's cooling law, that is for the Newton's convection, but here 3 laws are there. So one is the Plancks law, second one is the Wien's law, third one is the Stephen Boltzmann law. So Plancks law, so which is used to find out the monochromatic emissive power. Monochromatic emissive power means emissive power at particular wavelength. Okay. Wien's law, which is used to maximum monochromatic power, emissive power, or maximum spectral emissive power. Maximum spectral emissive power means spectral emissive power at maximum wavelength. So that is the difference. You have to identify that one. So third one is the Stephen Boltzmann law, which is used in the first unit for the finding of radiation. Okay. So emissive power, based upon the Stephen Boltzmann law, you can find out the total emissive power. It is the total emissive power means that is not related to wavelength. Okay. So you know that total emissive power means EB, it is represented by EB. EB is equal to, so integration of, we can find out the total emissive power by integrating the monochromatic emissive power by the help of the limits. So that is the limits. So 0 to infinity. Okay. 0 to infinity to EB lambda into D lambda. If you integrate this one, we will get the final formula, that is nothing but EB is equal to sigma into T to the power of 4. Okay. So it means EB is directly proportional to T to the power of 4. According to Stephen Boltzmann law, emissive power or total emissive power is directly proportional to 4th power of the absolute temperature. 4th power of the absolute temperature. So obviously remove the proportionality, we will give the constant, that is a sigma into T to the power of 4. This sigma is nothing but Stephen Boltzmann law, Stephen Boltzmann constant. So the value of Stephen Boltzmann constant is equal to 5.67 into 10 to the power of minus 8. You know the value. Okay. So this is the EB. EB is equal to lambda sigma into T to the power of 4. So finally, so based upon these 3 laws, we will get the 3 values. That is the, according to Plancks law, we can find out the monochromatic emissive power. Monochromatic emissive power is represented by EB lambda. It means emissive power at particular wavelength. Okay, by the help of Plancks law. Second one is the EB lambda max, maximum monochromatic emissive power or maximum spectral emissive power. It means emissive power at maximum wavelength. So that is the value. So that can be calculated by the help of the Wien's law formula. Okay. Last one is the total emissive power, that is represented by EB. Okay. So three parameters. So if the wavelength is considered, we can consider the either Max Planck's law or Wien's law. If the wavelength is not given, we can find out the emissive power by the help of the Stephen Boltzmann law. Stephen Boltzmann law, it is represented by EB, total emissive power. So sigma into t to the power of 4. So this one is the 12.87 into 10 to the power of minus 10 t to the power of 5. This one is the C1 by lambda to the power of 5 into exponential of C2 by lambda t minus 1. So these are the values. You have to remember these formulas to find out the required emissive power, or either a particular wavelength or maximum wavelength or overall emissive power. So these are the laws to find out the emissive power or rate of heat transfer by radiation. Okay, so this one also covered in previous first unit. So according to Stephen Boltzmann law, if the heat transfer takes place from one body to another body, it means heat transfer between the two bodies. First body temperature is equal to T1, second body temperature is equal to T2. Okay. So then the formula according to Stephen Boltzmann law, Q is equal to sigma into T1 to the power of 4 minus T to the power of 4. So this is the value. How to remember this one? If you can set the areas, you can write the area also. So if these are not a black bodies, if these are gray bodies, then you have to find out the consider the emissivity epsilon also. Okay. So finally, there are three laws. The fourth one is the Kirchhoff law. I want to explain that one also. Planck's law. So is used to find out the monochromatic emissive power or spectral emissive power. This is the formula. So the second one is the Wien's law. Maximum monochromatic power, emissive power or maximum spectral emissive power. So we can find out by the help of the Wien's law. Third one is the Stephen Boltzmann law. Total emissive power. We can find out the total emissive power by the help of the Stephen Boltzmann law. Okay. We'll see Kirchhoff law. Kirchhoff law is nothing but emissivity is equal to absorptivity. So emissivity is completely equal to absorptivity. Okay. You know that emissivity already covered in previous class. Emitting energy of a surface by emitting energy of the black surface. So our emitting energy of the any surface, either gray or something, by compared with the black surfaces. So you can find out epsilon into EB, emitting energy of the any surface. Okay. Now we'll see one numerical based upon these three laws. Okay. Calculate the following quantities for an industrial furnace. So that is, you can consider, if you consider black body, emitting radiation at 2685 degrees Celsius. So it means absolute temperature of the body is given. So that is the temperature is equal to 2685 degrees Celsius. So black body means epsilon is equal to 1. You know that. So you have to find the 5 points. First one is the monochromatic emissive power. You have to find out the monochromatic emissive power at given wavelength. What is the wavelength? 1.2 microns. Okay. So wavelength is given, means by the help of Max Planck's law, we can find out the monochromatic emissive power. Second one is the wavelength at which emissive power is maximum. Wavelength at which emissive power is maximum means that is called maximum wavelength. So lambda max. So you know that Wien's law, lambda max is equal to 872897 by T. So by the help of the Wien's law, you can find out the lambda max. Okay. So that is the second point. Third point, maximum spectral emissive power. Maximum spectral emissive power by the Wien's law, you can find out the maximum spectral emissive power. It is represented by EB lambda max. EB lambda max. This one is the EB lambda particular wavelength. This is the EB lambda max. This is the monochromatic emissive power. This is the maximum monochromatic emissive power. Okay, or maximum spectral emissive power. Monochromatic, spectral, both are same. Don't confuse that one. So about that one. So okay. Next one is the total emissive power of furnace. Total emissive power of the furnace. So here just like there is no wavelengths, total emissive power. So you can find out the total emissive power by the Boltzmann Law. Okay, you know that is represented by EV. EV is the total emissive power of the furnace. So this is next fifth point. What is fifth point? Total emissive power of the furnace. It means by the help of the Boltzmann Law, how to find out if it is treated as gray and diffuse body with an emissivity. So previously it was started with the black body. So in this point, if it is treated as gray body, gray or diffuse body. If it is black body, emissivity is equal to 1. You can take directly. If you treated as gray and diffuse body, so emissivity value has been given, that is the emissivity is equal to epsilon is equal to 0.9. You have to construct this one also. Okay. So you know that according to Kirchhoff law, emissivity is equal to absorptive. And emissivity formula is equal to total emitting energy of the surface by total emitting energy of the black surface. Okay. So black surface, you already derived this one. This surface where emitting energy you have to find out. It means E is equal to emissivity into EB. You know the EB value by the Boltzmann Law. Okay. So you have to find out this one also. Okay. So first of all, we will see the first point. What is the first point? Monochromatic emissive power at 1.2 microns. Okay. So it means lambda is equal to given 1.2 microns. Okay. So what is temperature? Temperature of the black body or absolute temperature is equal to T is equal to 268785 degrees Celsius. So here in radiation, so every temperature which is in degrees Celsius should be converted into kelvins, because here just powers of temperature will be placed in the radiation. So it means according to Boltzmann Law, E is equal to or EB is equal to sigma T to the power of 4. So it is the fourth power of the absolute temperature. So we have to convert the temperatures. So in Kelvin. Okay. So okay. Then you know that formula to find out the monochromatic emissive power or spectral emissive power based upon the Max Planck's law. So that is the formula EB lambda is equal to C1 by lambda to the power of 5 into C2 by lambda T minus 1. So this is the formula. You know that C1 and C2 is the constant values. Lambda values also given. So you know that temperature of the emitting temperature of the black, so furnace temperature. So you know the values. If you substitute these values, then we'll get the monochromatic emissive power. So the values of monochromatic emissive power is equal to here just like 2.53 into 10 to the power of 6 watt per meter square microns. Okay. So this is the value of monochromatic emissive power. So first point has been completed. So second point we will see. So what is the second point? That is the wavelength at which emission is maximum. Wavelength at which emission is maximum means maximum wavelength. We have to find out that one. You know that formula, maximum wavelength is equal to 2897 by T. Okay. So lambda max is equal to 2897 by T. If you substitute the value of T here, then you will get the lambda max by the help of Wales law. Okay. So third point, now we'll see third point. What is third point? Maximum spectral emissive power. Maximum spectral emissive power. Okay. So spectral emissive power, you know that by the help of Plancks Law, we already derived this one. Now you have to find out the maximum spectral emissive power. You know that the formula also, the maximum spectral emissive power by the help of the Wien's law is equal to 12.87 into 10 to the power of minus 10 T to the power of 5. So here you know that value of temperature. If you substitute this value here, then we will get the maximum monochromatic emissive power or maximum spectral emissive power. Okay. So last one, fourth one is the total emissive power. Okay. So you know the total emissive power, we can find out the total emissive power by the help of the Stephen-Boltzmann. According to Stephen-Boltzmann law, it is represented the EB is equal to sigma T to the power of 4. Okay. Sigma is the Stephen-Boltzmann constant, 5.67 into 10 to the power of minus 8 watt per meter square Kelvin to the power of 4. Okay. Into. So you know that T is the temperature of the surface. That one also given. That is the 2923. Okay, if you substitute these values in this formula, we'll get the total emissive power. Total emissive power value is equal to 4.139 into 10 to the power of 6 watt per meter square. So here Kelvin cancel. We'll get the watt per meter square. Okay. So last point. What is the last point? Total emissive power of the furnace. The condition. What is the condition also? Total emissive power of the furnace. If it is treated as gray and diffuse body. Gray and diffuse body means you have to consider the emissivity. If you consider the emissivity, so according to Kirchhoff laws on that one. You know that emissivity formula. Emissivity is equal to emissive power, total emissive power of the any surface by total emissive power of the black surface. So you know that EB or emissive power of gray body by emissive power of the black body. Then emissive power of the gray body is equal to epsilon into emissive power of the black body. Emissive power of the black body already derived by the Stephen-Boltzmann law. So the value of that one is equal to 4.139. Okay, epsilon value is equal to 0.9. If you substitute those values, you will get the final value. So here. Okay. So in this way, just like we can solve the different emissive powers. Emissive power at particular wavelength, maximum emissive power, total emissive power, emissive power for the black surfaces, emissive power for the gray surfaces. We can find out. Okay. So did you observe the comparison for the conduction and convection? In conduction only, just we have used only one formula, that is the Fourier's law for finding the rate of heat transfer. In convection, just we used the only one formula, that is the Newton's cooling law. But here, just three formulas are there because we have to find out the total emissive power, monochromatic emissive power at particular wavelength. So maximum monochromatic emissive power. Okay. So based upon these three laws, it means Max Planck's law and Wien's law and Stephen-Boltzmann law, we got the three formulas. By using three formulas, we can find out the emissive power at particular conditions. Okay, so that is the value. Now let's see just like emissivity. What is emissivity? Okay. You know that I already covered in previous class. So emissivity is equal to energy emitted from a surface. That surface may be a gray surface or another surface. Okay. So energy emitted from a surface, just like by energy emitted by black surface at the same temperature. At the same temperature. It means epsilon is equal to E by EV. EV is the total emissive power. E is the total emissive power of a any surface, just like gray surface. This is the total emissive power of the black surface only. Okay. So that is the formulas. You have to remember this one. So next one is the Kirchhoff laws. So what is Kirchhoff law? So that is the fourth law. This one also very important, Kirchhoff law. So this says that emissivity is equal to absorptivity. Alpha is equal to epsilon. Okay, you have to remember. According to Kirchhoff law, emissivity is equal to absorptivity. So suppose you know that alpha plus rho plus tau is equal to 1. Okay, some portion will be observed, some portion will be reflected, some portion will be transmitted. So if you consider the just like opaque surfaces, just like opaque surfaces, nothing but metal surfaces. For the metal surfaces, we will see only absorption and the reflection. We can't see any transmission of energy. Okay, so it means tau is equal to 0. Alpha plus rho is equal to 1. You know the alpha, according to Kirchhoff's law, alpha is equal to emissivity. Emissivity plus rho is equal to 1. Then rho is equal to 1 minus emissivity. Okay, so absorption rate is equal to emissivity. Reflection rate is equal to 1 minus emissivity. Okay, so now we'll see another surface, just like diffuse surfaces and gray surfaces. We'll see condition of diffuse surfaces. Okay, diffuse surface means the surface which its properties are independent of direction. Properties are independent of direction. Okay, for the gray surfaces, properties are independent of wavelength. Okay, for the gray surfaces, just like these properties are independent of wavelength. Okay? So most probably wavelength will not be considered. So automatically we use the Stephen Boltzmann law to find out the total emissive power for the gray surfaces. So thank you for this listening this class. In next class, I would like to explain about the view factors of radiation. View factor of radiation. What is the importance of view factor? Way how to study about the view factor. What is the functioning of view factor in the radiation? We'll see. Thank you for this listening this class. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.